All right, apologies in advance for this Smart Notebook Limited watermark. I don't know what's going on there, but we'll work around it. Our video today is on forces, which are kind of the crux of physics study, right? This is sort of the meat of our course, and it's part of what makes kinematics, right, the study of motion, interesting. So we get to put another wrinkle in our study of motion, which is pretty cool. So just to go ahead and define a force, right, is a push or pull on an object. Right, and to a certain extent, right, forces create motion, right? You know intuitively, right, if you push or pull an object, it's going to move, right? So forces are sort of the sneaky thing that's been behind our constant velocity and constant acceleration study, but we haven't quite gotten to them yet. Important to note here that forces are a vector quantity, right? So they have both magnitude and direction, right? They're going to have magnitude and direction. And we can also represent them with vectors, right? Like we have been doing for velocity and acceleration, which are both also vector quantities, right? So we can represent forces like this. The general symbol for forces is a capital F, right? And we'll sometimes do a little sub description here for the type of force that it is, but generally forces are capital F, right? And it's got this little arrow above it to indicate that it's a vector quantity. The unit for forces is a Newton, right? Named after this guy, Isaac Newton, who's pretty famous for a couple laws that we'll talk about shortly around forces. A Newton actually equals, to convert this, it equals a kilogram times a meter divided by a second squared. So kind of funky, this conversion, but this actually comes from an equation that you may have seen before, that is force, right, equals mass times acceleration, right? Mass can be kilogram, right? Acceleration we know is meters per second squared. But that's kind of an aside. Don't worry about that right now. Right, so our general unit for now is going to be newtons, right? Keep this in the back of your mind, this conversion, it's going to be important later. So there are two main groups of forces, two groups. The first one is called contact forces. Right, and that's, just as the name suggests, the force is exerted by touch, right, by contact. So when I, pick up this pen, that is a contact force that I'm exerting on the pen. The second type of forces are called field forces, right, and there's no contact in field forces. They're sort of invisible, hard to conceptualize, right? The biggest one that we're going to deal with is gravity, right? The force that's enacted on the object because of the mass of this giant Earth that we live on. Another common field force is electromagnetic force, right? So the force of a magnet. We're not going to talk too much about that, but it is one that you should be aware exists. So when we start talking about forces, like when we talked about motion, we have another diagram that we want to talk about, right? So we have this thing called a free body diagram. Free body diagram. And just as in CVM or CAM, we had motion maps and graphs, right? This is essentially a pictorial model of force, right? So it's a, what do you call it? Pictorial model. And it just sort of helps us wrap our brain around what's going on in a system and what forces might be at play, right? So say we have a ball that's hanging by a string, right? It's suspended by a string, and we want to draw a free body diagram for this, right? The first step to draw a free body diagram is to define the system, right? What are we concerned with? Because if our system is the entire Earth, we're going to have a lot of forces to deal with. So I'm going to go ahead and say that we're concerned with, we're not really concerned with the string attached to the ceiling, although we could be. I'm just going to say that my system is the ball, right? So this is my system that I've defined, right? The ball. And then next I'm going to want to figure out what contact forces are acting on the ball, right? Contact. And the big one is the rope, right? So there's going to be some force of the rope. And then I'm going to want to think about field forces, right? And because this is presumably happening on Earth, we're going to have some force of gravity. So my free body diagram, I essentially represent the system as just a dot, right? So I've taken everything that's in this red circle and sort of polished it down to just a dot. This is my system. And then I'm going to represent the forces as vectors, right? So you represent forces as vectors. And you want to show the vector pointing in the direction that the force is acting on the system, right? So for the rope, right, the rope is pulling up on the ball. So the direction of the force is going to be a pull up, right? So the head of my arrow is going to be upward, and this is my force of the rope, right? The ball is also experiencing a push downward, right, from gravity. So my downward push is going to be gravity. Again, my vector points downward, okay? So that's how you draw a free body diagram, right? I want you to go ahead and try for a second to draw free body diagrams for these two scenarios. Number one is going to be a flower pot falling from a window. And number two is going to be let's say, your textbook on the table, right? If you have a textbook on your desk. So using this sort of idea, define the system, right? In both these cases, you're going to want to keep the system small. So I'm going to say, this is the flower pot will be my system and the textbook, right? And see if you can identify what forces are going to be acting on these things and draw free body diagrams. So go ahead and pause the video, go ahead and sketch these in the notebook, right? And then I'm going to go over them when you get back. So hopefully you've had a chance to sketch these in your notebook. So I'm going to go ahead and do the flower pot, right? I'm going to reduce the flower pot to just a dot, right? And this flower pot is falling from a windowsill, right? So it's in free fall. There's nothing contacting the flower pot except for the air, and we're going to ignore air resistance. I should have mentioned that. Right, so there's nothing in contact with the flower pot, right? There's no external thing touching it, so there's going to be no contact force, right? But there is a field force, right? It's experiencing some downward push from gravity. Right, so we're going to go ahead, draw a little downward push, Fg, gravity. So you should have a free body diagram that looks like that. Now for the textbook on the desk. Again, I'm going to make my system my dot, right? Is there any external force touching the textbook, right? In this case, it's the desk, right? The textbook is sitting on the desk. So the desk is exerting some upward force on the textbook, right? Force desk. And then assuming we're on Earth, right, there's some force of gravity, right, or force of the mass of the world, right, which gravity essentially is, pushing down on the textbook, right? So that's my free body diagram for the textbook, okay? So these are going to be really, really useful. Another sort of convention thing about these free body diagrams, right? Once you identify your forces and what direction they're going, you want to define, what direction is positive or negative, right? Generally, make a note. Unlike with motion, right, where we generally said up was positive, down was negative, right? With forces, you want to say that the positive direction follows the greatest force. So if in this case, right, if for some reason the force of gravity were significantly larger than the force of the desk, right, my positive direction would actually be down, right? I would want to say positive. And in part, this is because when we add these together, which we'll get to next time, right, having a negative force doesn't make all that much sense, right, which we would if this were the positive direction. So you try to define your axes, define your system, right, your coordinate plane, so that the largest force is a positive one. Therefore, you're not going to have a negative net force, right, which is somewhat confusing. So the goal of this, it's not the end of the world if you screw this up, but you want to kind of prevent negative forces, right? Total forces on an object, right? And part of this we'll get to next time is around combining vectors, right? So if we wanted to figure out the net force on this desk, right, in this scenario where gravity exerts a greater force, right, we would add them head to tail, right? So we would add Fg, right, to Fd. That's Fd, there's Fg, right? And the net force is going to be, right, the connecting vector that connects the tail of Fg to the head of Fd, right? So this red vector here is going to be Fnet, the net force. But we'll talk more about that next time. But the goal of defining these axes is really to make sure that this Fnet isn't negative, because it's hard to think about a negative force. It doesn't really sound right. So go ahead and wrap your head around these free body diagrams. If you want more practice with creating free body diagrams, there are some questions in your book on chapter 4.1, I believe. This is all in chapter 4, which is, I think it's called Forces in One Dimension, right? So we're starting with forces in one dimension like we did with motion, and then we'll move into forces in two directions, just as we did with motion. All right. See you guys later.